So last time we were actually looking at the properties of spiral galaxies. We were looking at the surface brightness, isophotes, and stuff like that. So as I mentioned, a lot of properties of galaxies are correlated with each other, like mass, their morphology, their color, their star formation rates, and so on. So this is sort of these are tables from the book, and you can actually see that even in the sequence of spirals, you have some patterns. Okay, like S0, SA are generally older stars, less blue compared to SDSM, like going down the sequence in the Hubble tuning fork. So you can actually just look at this. Similarly, here are some recent data from something like SDSS, Sloan Digital Sky Survey. This this observational program has actually looked at hundreds of millions of galaxies and measured their colors and other properties, morphological type, and so on. So you can actually see. So this is morphological type, elliptical to S0, SASB to irregular. This is something like coarseness. Deviation from a smooth image, right? Coarseness is defined as, so if you have things like spiral arms and so on, that is deviation from smooth image. So what it means is that, see, there is a large scatter at one point, but the median has a trend. So you should always remember that these are only average trends. These are like, it's not like always you will have a spiral galaxy will always be blue. That's not the case. It's a population statement, right? It's not like everyone who's a Scandinavian will be tall. You can find short people in Scandinavia, and not everyone in, say, whatever, the country where people are generally shorter, you can find very tall people there too. So in the same way, galaxies have this diversity. So when we make these statements, we are making average statements about the median population. So you should always keep this in mind. Galaxies are complicated things. They are not like, it's not like, so there are two kinds of processes that we study in physics, right? One is like basic physics, fundamental things, things like quantum mechanics and all that. The other is the complexity, chaos, and things like that. In the chaotic and complex systems, you don't have very precise patterns, generally speaking. Okay, so these galaxies are also very complex systems. So we can only make statistical statements. Okay, let's move on. So I had mentioned about this. If you look at the spectra of galaxies, it's sort of like a sum of spectra due to the stellar population in that galaxy modulated by dust. So, for example, here are some galactic spectra. So, this is x-axis is wavelength, y-axis is flux. So it should be easy for you to tell which one is a young galaxy. So out of these four, which one is a young galaxy? Just quickly tell me, the top one or the bottom one? Top, because it has a lot of light and shorter wavelengths. And there are these, you can actually see there are a lot of absorption features like in stellar spectra, but you see emission lines as well. Right? Normally, stars do not show emission lines. So you can get emission lines either from AGN, the vicinity of the black hole, or from the gas around stars, which is excited by starlight. Things like H2 regions, nebulae. You must have seen HST images of these beautiful nebulae, right? They like glow in those in different colors. So these are nebular emission lines, either from stars, powered by stars, or by AGN. So anyway, you read the book and get details of these things from there. So in today's class, we'll actually be learning about little bit about the understanding of spiral arms and bars, right? A lot of galaxies have very prominent spiral arms, right? If you look at, say, for example, here, this is a galaxy M100. This is a B band image, and this is an I band image. B is sort of blue, I is like close to red, infrared. You see the I band image is smoother compared to B band because I band image sort of mostly is dominated by old stars, red stars. So whereas the young stars form where the density is the highest, and so these are the places where you have like highest star formation, a lot of young stars. So these are spiral arms. Spiral arms has a lot of dense gas, a lot of dust, and a lot of star formation. Okay, now the bottom figures are the same galaxies, but we are seeing colors. So here in the top figures, gray or dark is higher brightness. Okay, here these are complicated figures. So there are two kinds of features here. One is the dark, the color scale. So the color scale here shows the B minus K color. So if B minus K color is small, B minus K color being small means the value of B band magnitude is small. That means it's brighter in blue. So wherever this is large, that is wherever this is white, you have stars. So you can actually see these spiral arms actually are correlated with the white patches here. So it's bright in B band and its color is blue. And what you also have there are contours. I think here they're not very easily visible. You should look at the book. The contours show the H alpha emission, right? So where does this H alpha emission come from? Quickly, I've told this. H alpha is not, yeah. So yes, stars, young stars excite these H2 regions which emit H alpha. So you can actually see these contours sort of being highest close to where young stars are. Here you see H1 contours. Here you can actually see them. They are much larger scale contours. That means H1 emission due to 21 centimeter hyperfine transition in neutral hydrogen is visible on a, it is more diffuse compared to H alpha emission. And I think the gray scale is the same in the two colors. So these kind of spiral features are called grand design spirals. Such galaxies are called grand design spirals because you can actually follow a single spiral arm for a large angle, right? So if you go, you can actually see this one. You just go out. You can still follow it in these broadband images. Similarly here. But in contrast, you have galaxies like this. Here, you cannot really follow a single feature very long. It just becomes, it just gets cut off. These kind of galaxies are called flocculent galaxies. They don't have these very open and large in angle and in radius spiral arms. So these are flocculent galaxies. This has nice spirals, but you can only follow it for 180 degrees or so, not more than that. But more importantly, there is this feature which is called the bar. So you have the bar at the center. Of course, you have the bulge. This very bright thing at the center is the bulge. This is the bar, and the bar a lot of time looks like is connected. Bar is end of the bar is where you have these spiral arms emerging. In fact, they have a very deep connection dynamically. So that's why, even dynamically, we expect the bar to be the end of the bar to be the starting of spiral arms. The dynamics is actually quite hard. We still don't have very good understanding of how the spiral arms are maintained and produced, and also also the details of dynamics of the bar. So this is a current research topic. Okay. So we'll do a little bit of writing now. So one of the puzzles, it's very important to recognize that these spiral features that you see in these stars are not the so-called material arms. So what is a material arm? It's not like, if you have, say, smooth gravitational potential of a galaxy, if you arrange stars in form of a spiral at some time, okay, and you let it go, right? The stars are going around in circular orbit in disk galaxies, but there is a differential rotation, right? It's not like a solid body. If galaxies were solid body rotators, then you can arrange a spiral and it will just happily maintain its spiral shape. But a real galaxy has differential rotation, right? If you have a flat rotation curve, right, v phi being constant as a function of radius, in that case, omega, which is v phi divided by the cylindrical radius, goes like 1 by r. So the inner stars are going faster in angle compared to the outer star. So if you put anything at t equal to 0, it will get sheared, right? So that's why it's a tricky question to answer. Why do you have spiral arms? Okay, so so we will actually do a little bit of working out. Okay, so let's see. First we draw something. So let's see. So you have a galaxy. This is a some sort of a spiral feature. Okay, and this is some circle of some radius. So you can actually write the equation of the spiral in this r phi plane. So cylindrical coordinates are natural coordinates for spiral galaxies. So cosine of, so let me actually write something, cosine of m times phi plus some function of r and t is equal to 1. Okay, so this is this is like some equation that describes the locus of the spiral arm. For some, this phi is the cylindrical angle, so you can actually say, the r phi, and so it's z equal to 0 plane. Okay, so what does it show? That for a fixed radius like this dotted line that I've drawn here, for a fixed radius, and say this fr does not depend on time, right? Let's forget about the time dependence for now. So at a given instant now, this has some, and at a fixed radius r, this is a constant value. So this function is periodic, is m-fold periodic, right? As phi goes from 0 to 2 pi, it will have m waves, right? Full orbit. So m equal to 1, if you say plot as a function of phi, so it's sort of 0 to 2 pi. If you have a cosine function, and let's say, this is 0, or, so that cos function is easy for me to draw. So this is, I'm sorry, but the drawing is not the best. But so this is a cosine function. So this is a 1 wave. So this is m equal to 1. So what does it mean? So as you go around this circle, so you will have one maximum and one minimum in intensity, for example, right? And so this is not an m equal to 1. So if these are like, this is like a density of stars, this is an m equal to 2 mode, right? Because you have a maximum here and a maximum at pi, not at 0 and 2 pi. So if you just had a single arm, that would be an m equal to 1 feature. Okay, so this is actually simple. So this is actually an example of m equal to 2. M equal to 2 spirals are very common, right? As you go around 2 pi, you have 2 maxima in the intensity, right? All these examples that I showed had, a lot of them. Actually, not the flocculent ones have a lot of m, have a very high m, but the other guy, which had an arm, had actually m equal to 2. Okay. So I was actually mentioning about this winding problem, right? That even if you arrange a beautiful spiral at t equal to 0, it very quickly gets sheared and becomes like very tightly wound. So let's actually see that mathematically. So let's see. So this is, at this point, this is the tangent to this circle. Okay. So if you draw a straight line, this is 90 degrees. And this is the local slope of the spiral arm. So this direction that I've drawn here is so this angle between the tangent to the circle and the tangent to the spiral arm at that point is called an inclination angle. So if you just say if I is 0, you have very tightly wound spiral, right? I close to 0 means that the spiral arms are almost parallel to your circle. So let me actually draw like a simple example of a very tightly wound. So if you have if you have a feature like this, here the eye is very small, right? You can actually see the contour of brightness, high brightness, actually coincides with almost a circular contour. So this has a very small eye. So the SC, SD, and grand design spirals are of this kind, which have a large eye, and the flocculent ones and very tightly wound spirals are of this kind. Okay. So this is the inclination of the arm. So let's see. From geometry, tan of I is equal to. So if you go locally, the tangent of I is the ratio of dr by rd phi. Let's see if that makes sense. So as you go around the spiral arm, so dr is how much you move radially across the circle, and rd phi is how much you move as you go along the spiral. How much do you move in angle phi? So this is the distance traveled perpendicular to the dotted circle. This is the distance traveled along the dotted circle, and this ratio is tangent of phi. Simple geometry, local slope. So if this is the locus of your spiral arm, how do we calculate the inclination angle? So let's see. So 1 by tan I. If my writing goes out the screen, just let me know. Is equal to so r dou phi by dou r. This is calculated along this spiral. So how do we? So if this is the equation of the spiral. So how do we calculate this? So this is nothing but r times Dou f by dou r. Actually, we'll just put a magnitude here because the sign is not important. Okay. So this is just coming from differentiating this, right? Where the phase is, you are moving along the spiral. That's why this phase function is constant as you move in phi and r. So this is the value of inclination. So so let's see. So so let's take the simple case of phi equals phi naught plus omega r times t, right? So so at t equal to 0, this angle phi, this one describes at t equal to 0, you have say, this is the, the radial feature is where you have brightness, high brightness. And at t equal to 0, phi equals phi naught. That's the locus of high brightness. So this is this. But at later times, this inner part will move faster and go ahead, and the outer part is moving slowly. So quickly, this guy will be sheared out into a something called a trailing spiral. So, right, because this is the direction of rotation of orbits, and this is the direction in which the spiral arm points. So this is called a trailing spiral. Most of the observed spirals are actually trailing spirals in the sense that the orbit of stars and gas is in a different direction than the pointing of the arm, right? And you naturally expect if these were rigid or these were like material features, these kind of things would be sheared into a trailing spiral, because the inner guys will move ahead and the outer guys will stay behind, forming a trailing spiral. But you do sometimes, rarely, also see leading spirals. Okay, so so if you have this, I mean, in case, so this is basically just writing this thing inside these bracket, right? We are sort of not bothering about m here. If this is constant, phi plus f is constant, then your intensity is constant because it sort of is a cosine of something. So let's see, if we use f as this omega r times t, what does tan I look like? So tan I would be, so so 1 by tan I, let's see, is equal to, dang, we have run into the problem or not? No. Yeah. So 1 by tan I is r times, so this is your, f, this is sort of your f. So let's do, so this is d omega dr times t. So this is your 1 by tan I. So what it tells you, as your time increases, your tan I decreases, right? So, or I decreases. So if you start with this case, what is I for this initial condition? Right, it's pi by 2, because if you go along the arm, the angle between that and the circle is 90 degrees. But with time, tan I goes like 1 by t. It gets, I becomes smaller and smaller with time, and if you wait long enough, I can go to 0. Right, so that's what you expect. So if you plug in the numbers, and if we put, say, the age of the galaxy is, say, 10 gigayears, if we put this in, then what do you expect for this? So we know the rotation, right? We know the rotation velocity, the flat rotation velocity of Milky Way is around, say, 200 220 kilometer per second. The omega, of course, is this divided by r. If you plug in r of 10 kiloparsecs, and if you do the math, what you will find out is in 10. So, in other words, the sun has gone around the Milky Way for few tens of times. Okay, so that's how much the inner guys will move, even more, right? The sun is not so inside. So the inner guys will move many, many, many times, and the outer ones won't. So it will actually cause this to be a lot, become wounded. And if you plug in the numbers for t equals 10 gigayears, what you get is inclination angle is about 0.14 degrees. 0.14 degrees is like 1 degree. You've seen the protractor, right? 1 degree is tiny. 0.14 is like nothing. It should really be like circles, but that's not what we see. So this is the winding problem. This is called the winding problem. So this is the case. So this is the equation for a material arm, right? In the sense that omega, so the equation of this is as if in time is as if you have arranged high density of stars at t equal to 0 along a radial line, and then just say that this high density just follows the dynamics, which is rotation at local omega. But if that is the case, you quickly see that it will be very tightly wound spiral, which is not the case. So these spiral arms cannot be material arms. This is the conclusion of this exercise. So what are these? So actually think of spiral arms as, there's a very good analogy with traffic, right? So imagine a red light in traffic, okay? So you have cars which are sort of like stars coming towards the traffic light. If the traffic light is green, everything sort of moves smoothly. But if you stop the cars at a traffic light, what you'll see is that there is an excess of cars just after where they stop. And this jump in the density of cars moves backwards in the direction opposite to the direction of the cars. So this is an example of something which is a pattern, which is like, moving at a different speed compared to the constituent particles, constituent things like cars. So what we should think of spiral arms as a pattern which is moving independently, essentially, of the stars. So this solid, this solid body rotating material arm is not the right picture to look at spiral arms in galaxies. So how do we resolve this winding problem? You can have so basically what you need is you need to produce these radial features, right? And these radial features can nicely be, sheared into trailing arms. If you can produce these radial features on a short time scale quickly, new arms are, so new things are coming, and then you're shearing slowly. So this is a good picture for flocculent galaxies. So there is some process which has to have some gas and self-gravity. So the gas and self-gravity are extremely important for spiral arms. Self-gravity of the gas is what maintains these dense features. So you can actually form flocculent galaxies by in that way, that self-gravity produces these radial over densities and they get sheared. But what about grand design? A lot of these grand design spiral galaxies have actually a companion. So because of the companion, the grand design pattern can actually be excited. So the standard model for spiral arms is something called the Lin-Shu, and actually Lindblad also. density wave theory. So this is sort of the, whatever weak understanding that we have of spiral arms, this is sort of the basis of that. And the idea is this traffic analogy that I mentioned, that these spiral arms are some sort of a wave pattern, okay? So you have stars which are going around in circular orbits. So there are stars which are not in the spiral arm now. They go, and as soon as they see this traffic jam, which is the spiral cities, and they get sheared. But what about grand design? A lot of these grand design spiral galaxies have actually a companion. So because of the companion, the grand design pattern can actually be excited. So the standard model for spiral arms is something called the Lin-Shu, and actually Lindblad also. Density wave theory. So this is sort of the, whatever weak understanding that we have of spiral arms, this is sort of the basis of that. And the idea is this traffic analogy that I mentioned, that these spiral arms are some sort of a wave pattern, okay? So you have stars which are going around in circular orbits. So there are stars which are not in the spiral arm now. They go, and as soon as they see this traffic jam, which is the spiral arm, they are still going at the same speed, but their densities become high at that location because of self-gravity. So a star starts away from the spiral arm, it enters the spiral arm, slows down a little bit, increases the density, and then exits it, okay? So just like a traffic jam, cars, not the same cars will be stuck in the traffic at the signal. But that traffic will stay at that place. In the same way, the spiral arms are not moving very fast compared to the orbits of the stars. They are much slowly evolving, but the stars become part of it and then leave it. That's the picture. So it's some sort of a wave pattern which evolves more slowly, much more slowly than the orbits of stars. This has to be extremely clear to you. Okay, so we'll not go into the deep mathematics and dynamics of these spiral arms, which is a complicated topic in itself. But we will actually learn a little bit about this, especially the version of this theory which is called kinematic density wave theory. Okay, here we'll not talk about the dynamics of this, but talk about, suppose you arrange things in a certain way, can you sort of justify this? Can you sort of solve the winding problem? Okay, so we'll do the kinematic density wave theory. Okay. So for this, we need to know a little bit about dynamics. We'll actually be doing dynamics of stars in extended potentials, right? The gravitational potential of spiral galaxies or galaxies are extended, right? And if you have done Goldstein level classical mechanics, you know that there are only two potentials for which you have closed orbits, right? If you have phi, which is -1 by r, this gives you Kepler's orbits. And which is the other one? No, yes, r squared. That's right. Harmonic oscillator potential. It gives you closed orbits. But in general, if you have a galaxy, say Milky Way, which is a flat rotation curve, it is not one of these. It is a general potential. So what happens in a general potential? The orbits don't close. So they are the so-called rosette orbits. So you'll have, let me give you like a very badly drawn examples. So you can have orbits which just sort of don't close onto themselves, right? So these are called. So I have not drawn it properly, but this is actually an important idea that for a galactic potential in general, you won't have closed orbits. Okay. No, it's plus r squared, right? Potential, it's a positive, right? It's a harmonic oscillator. So force is minus d phi dr. So that gives you minus kr. So it should be a plus sign. Yes. So yeah. In galaxies, if you smooth out over stars, it sort of gives you how does the mass density vary as r to zeroth order. So this is the potential that we are talking about, or for that matter, dark matter. How stars and dark matter are made up of discrete objects, but the most of the gravity felt by them is not due to the nearest neighbors. Gravity being a long-range force, it's this global gravitation which dominates over small-scale fluctuations. So we'll actually come to that later. So all the stars and dark matter, everything. Okay. But the point is, you will not have closed orbits. If you put a test particle in a galaxy, it will not be like a beautiful Kepler's orbit. It will be like a rosette orbit. So it will just start filling. Given its energy, it will sort of start filling all the phi available in that sort of a band. Okay. So there are two. In such a case, there are two important things. So there is the radial oscillation frequency, which is 2 pi by tr. So tr is the radial oscillation time period. So say, for example, you have this as a circular orbit. So your star starts here and it goes up and comes down, and so this time is tr, the time that this star takes to go. So it's r relative to this circular orbit increases, decreases, and comes back at the same r. So this time is tr. Okay, and let's actually define omega a, the azimuthal variant of this. This is so let's see. Let me just write down. So delta phi by tr. So in this time, how much does it move in angle? So let's say this is how much it moves in angle. So this is delta phi. So if omega a equals omega r, delta phi is 2 pi. That's the Kepler's orbit. If you have a potential which is minus 1 by r, you have a, right? So we'll actually come to this. This is called the epicyclic theory. So this, and the Kepler's orbit is something like this. I'm not drawing it nicely, but you get the idea. So from here, it comes to the minimum distance from this center of the force and comes back again. So this is a tr, but t phi is the same, because in the radial period, it also covers 0 to 2 pi, right? For a harmonic oscillator, the things are somewhat different. I think in that case, harmonic oscillator, okay, so this is Kepler, which is minus 1 by r. Harmonic oscillator is something like this. It sort of has an orbit like this. In that case, this is the center of the potential. Yes? Oh, okay. Thanks. So this is, thanks for telling me. This is harmonic oscillator. Here, the orbit, if you solve the dynamics of this, we'll actually do a little bit of this. It looks like this. So this is an ellipse, but unlike this, where the center of the force is at one of the foci, at the focus, here it's at the center. Okay, so here the radial oscillation time scale is, here R is maximum, here it's minimum, here it is again maximum. So the radial time period is going from here to here. It only goes half the pi, half the 2 pi, and so it's omega R is equal to double of omega azimuthal. Okay, so these are the definition of these two frequencies. And for a rosette orbit, they don't have this nice integer relationship between them. Okay. So what is the idea? What do we want to do? We want to go, so you have these rosette orbits, and what you can actually sort of think of is, say you have this circular, and then you have perturbations around this circular orbit. So we will actually do something called epicycle theory, in which we actually look at almost radial orbits and fluctuations around that. So it's like a perturbation around circular orbits, and so for example, these are exact solutions, right? The Kepler solution and the harmonic oscillator solution are exact solutions. You can actually be an extreme ellipse, with a very high eccentricity. These are correct, but in the local limit, you will solve for the radial and the azimuthal oscillations, and you get sort of a good approximation in such a thing. So let's see, we start here, okay, and so in a single radial orbit, how much is the angle? Actually, this is what we have already shown. So in a single radial orbit, how much is the angle that you move? Delta phi. Okay, so what we want to do now is go to a frame which is rotating. Okay, so all this is done in lab frame. If you go to a frame which is rotating, in that frame, delta phi p, this is delta phi in the lab frame, delta phi p is equal to delta phi minus omega p. Omega p is the pattern speed, rotation speed of this frame at which this pattern is moving. Okay, so this is omega p times tr. So in a single radial orbit, this is how much your angle move. So this is in the lab frame. Suppose you go to a frame which is rotating at this speed, right? So then you will have an oscillation which is only a radial oscillation. So this will be 0 in that case, right? If your omega p is equal to omega azimuthal, then this will be 0 in that case. So if you go in that frame, the star will just do this. Okay, important to keep this in mind. So the idea is you choose this omega p so that the orbit is closed. Unlike a rosette orbit in a lab frame, you want to go to a rotating frame in which the orbit closes onto itself, and you can always do that. Okay, say the orbit closes onto itself after m radial oscillations. So after m radial oscillations, you come back to the same position in phi in this rotating frame. Okay, so that's what we are saying. So what does that mean? So this is this angle moved. So so 2 pi omega a times tr. This is the angle phi moved, minus 2 pi omega p tr. This is this term. This is the first term. How much does it move in angle in a single radial period? if this is equal to 2 pi times n by m, right? What it means is that in m radial orbits, you will make n phi orbits. Okay. It will be closed. It can be closed in this way. So it's in this frame. It's closed in this rotating frame, in this frame which is moving with pattern speed. Okay, so you can actually have a situation like pattern speed is, say, this, right? So this has, so how many radial orbits do you have? One. But this is closed in that rotating frame, not in the lab frame. If you have, that's one type of rotating frame. This is a general equation. So basically what it shows is that you make m radial orbits. So for example, here, what is m? So this is 1, 2, 3, 4, 5. Okay, and so here m equal to 5, and how much does it move in phi? So in this also, right. So I'll actually show you examples. Maybe I can show that now for different m and n. Say, for example, here. Okay, so this one is n equal to 0. It makes no orbit in the phi direction in this frame. Okay, so this one is just radial oscillations. It does not go full 2 pi in the phi direction. This one, this dotted line here is 1 comma minus 2. So for one, so for minus 2 radial orbits, so I think it's sort of taking care of the phase. So left 0 comma 1 is solid line, 1 comma 2 is dotted line, 1 comma minus 2 is the dashed line. So this one. So so let's actually look at this one. Okay, so here, so 1, 2. So from here, its radial distance from this is maximum. It's maximum. So from here to here is its radial period. And it takes 3 radial periods, right? You can see 3 maxima. It does 2 phi orbits. So that, these are little more general than the example. So the example that I was giving you was this one. But in all these cases, you form these closed orbits. Okay. In this rotating frame. Okay, let's go back here. So the condition for closed orbit becomes omega p equals omega a minus n by m times kappa. So this radial, so right, so the lab frame rotation frequency is omega, right? This omega as a function of r, we have actually encountered it. The radial oscillation frequency is something called epicyclic frequency. This is called epicyclic frequency. And for a Kepler's orbit, kappa and omega are equal. Okay, for harmonic oscillator, kappa is double of omega, right? It does 2 radial orbits in a single phi orbit. So this is called the epicyclic frequency. This is just, this is nothing but this guy, omega. This is equal to omega r. So if you can arrange that, this omega r minus some n and m, they can actually be negative or positive either. They're relative sign. If this value is equal to the pattern speed, in that frame, in that rotating frame, you will form closed orbits. Okay, good. So then the thing is, different radii right? Because this is a function of r. Similarly, the epicyclic frequency is a function of r. So you're at different radii, you will have different pattern speed in which you will form closed orbits, right? Because all these are functions of r. Now the trick here is to find an omega p which does not vary much with r. If you can find a combination of n and m for which omega p evaluated in this way does not vary much with radius, in that frame, your features will not be sheared out so quickly, right? So instead of omega, in the previous example that we were considering, where we were considering material arms, omega has some radiation with r. But if we are able to arrange n and m where the variation with r is small, then we can actually maintain the spiral arm for a longish time, for a longer time. So that's sort of the idea. Yes. Yeah, so I think these all then can go, right? Not really, right? This is like one orbit in a single radial orbit. So when omega t is equal to 1, that's one orbit, right? Right. So n is the number of m is the number of orbits in the radial direction. N is the number of orbits in the phi direction. So I think these are numbers. So this is angular frequency, not nu. 2 pi by t, no? Right, but both of these are ratios, no? This is ratio of integers. So 2 pi on top and 2 pi at bottom just cancels. Yeah. So I think I should not have just put any 2 pi anywhere. But it's sort of a simple thing. You can think about it. I don't think there should be 2 pi anywhere. Okay. So let me actually go to go here to the slides. No. Not. Yeah. This is good. This is good enough. Right. So this is just showing the winding problem. We've actually talked about this. Okay. Here is, yeah, so this is this condition of pattern speed being equal to this value going to a frame in which you form closed orbits. Now this is how does this guy omega minus n by m kappa, which is the epicyclic radial frequency, how does this vary as a function of r in, say, Milky Way galaxy? So these are these numbers that are written here. These numbers that are written here are, say, this is how omega goes as a function of r for Milky Way, right? So flat rotation curve, omega goes like 1 over r. So this sort of at large radii goes like 1 over r. If you put 1, 2, so omega minus kappa by 2, right? So 1, 2 will give for pattern speed omega minus kappa by 2, right? So if you look at 1, 2, this is the curve. It is almost flat. That's what I said. If your pattern speed is something which does not vary much with r, you can get a feature which does not get sheared out so quickly. And these are different combinations of n and m. So this is a very special case, 1, 2. This is m equal to 2 spiral feature. Okay. So these curves, you find the rotation curve for the galaxy, and there is a way to calculate the epicyclic frequency. We'll actually do the epicyclic theory later. So you can find both omega as a function of r from rotation frequency and kappa as a function of r from that, and then just plot these. So you are interested in the patterns which are very flat, because those are the modes. If you arrange at t equal to 0, they will not be sheared out so quickly. Okay. So n by m equals half pattern is relatively constant. Spiral won't be sheared out in that frame. So if you look at this expression, so from dynamical theory of this, this condition is called the resonance condition, right? So if you have a forced oscillator for certain frequencies, close to the natural frequency of the oscillator, you can excite very large amplitudes. So in the same way, this is a sort of a resonance condition at which you can excite these global waves with large amplitudes. So we are not doing the dynamical aspect of this theory, but there is a connection of this kinematic condition of closed orbits with the dynamics, which suggests that these can be important non-axis metric features. So go back here. So there are, like, if you put n equals to 0, so n equal to 0 is something called, basically n equal to 0 gives omega p equals omega, the rotation frequency. This is called corotation resonance. Corotation resonance. So what it means is that when the pattern speed is equal to the rotation speed, this epicyclic term does not matter. So this resonance. So this is one of the resonances, and then you have m times omega minus omega p is equal to kappa. These are called Lindblad resonances. So you can have n, right? So n comma m equals 1 by 2 was this important 1 comma 2 was an important case that we talked about. So as I already mentioned, these have dynamic importance as well. So the upshot of all this discussion is that if you can arrange a spiral arm at t equal to 0 for this 1 comma 2 mode, then you can go to a rotating frame in which the arms are not sheared very quickly. Or in other words, in the lab frame, this thing will rotate at omega p. You will still have closed orbits, but it will rotate much more slowly compared to the orbits of stars. So just look at these at your leisure and convince yourself that these labels make sense for such orbits. Okay. Now here is, so here I've drawn this horizontal line, and this horizontal line actually would cross this omega, this n equal to 0 case will somewhere. So that would be co-rotation resonance. So this is so you can actually look at constant pattern speeds and see if you are hitting any resonances. So wherever you put it, you will actually hit a point for each of these n comma m. You'll hit a point where you get a resonance. So for example, here what I've drawn, these, this is omega minus kappa by 2 equals omega pattern, which is this. So these are the inner Lindblad resonance. And so the outer Lindblad resonance is where, the resonance point which is outside the corotation radius. So if you say draw this this as your constant pattern speed, this one will be the corotation radius, resonance. This will be some sort of an outer Lindblad resonance. So anyway, we are not going into the dynamics of this, so we'll just move on. Right, so those are like a driven oscillator resonance. Those modes can actually be excited. No, spiral arms are like those high amplitude oscillations corresponding to those natural frequencies. Okay. So it's also observationally very difficult to tell apart a leading arm and a trailing arm, right? What is a leading arm? If the sense of rotation of stars and gas is the same as the rotation of the arms, this is a leading arm. This is a trailing arm, okay? And if so, this is a if you observe it at different angles, their observational signature. So this shows the in-plane rotation curve. So here, gas is receding away from us. Here, the gas is coming towards us. If you look at it appropriately from a particular angle, you can actually get the same appearance of the arm and the same sense of rotation. So you can't tell a leading arm easily apart from the trailing arm. So it's not very easy to see this in this figure, but if you draw something like a spiral arm and a rotation and actually try to visualize it from different angles, you can actually see that this does make sense. So I did it for myself, and you can actually see this. So what do you do in this case? So this is what you do in this case. So suppose we are observing from here. These stars are not obscured by the dense disk of this galaxy, right? They are between the dense disk and us. So these guys will not be reddened due to the dust in this galaxy, whereas these stars will be reddened by the dust in this galaxy. So if you look at them in the sky, you will see these things which are not as reddened, and you will see these guys which are very reddened. So then you know which side of this galaxy is pointing towards us, and then you can actually figure out whether it's trailing or leading. This is how you tell this apart. Okay, so here is an example of this kinematic density wave theory. So let's say you have these ellipses. Okay, all these curves are ellipses, not very eccentric ellipses. Here, all of them have their semi-major and semi-minor axes aligned. Here, you sort of rotate as you go out. You rotate the semi-major axis a little bit relative to each other. So these things get bunched. If you look at, so this is at t equal to 0. These guys get bunched if you rotate it a little bit relative to each other. So you can, by choosing your initial displacement in angle appropriately, you can actually make a leading spiral or a trailing spiral. Okay. Now the point is, if n comma m equals 1 comma 2, then if you arrange such a thing at t equal to 0, this will not be sheared as much because this is almost a constant. It almost, in this frame, this pattern rotates like a rigid body. If this was perfectly constant, it will never be sheared out. But since it's not, it's close to a constant, it shears out very slowly. So you won't get 0.1 degree in 10 gigayears. You'll get a much less angle. Right, so here is that value. So in 10 gigayears, the pitch angle in this case, basically you have to do this calculation, omega minus half of epicyclic frequency, then you get a 5 times larger. So this still does not explain the observations though, right? From from 0.15 degree to if you go to 1 degree, you're still very, very tight. So things are not totally satisfactory. So the understanding now is that a lot of these spiral features are very short-lived, right? So you excite them some through self-gravity, and they're like consistently getting sheared out. But if you can excite them much faster, then the older ones get sheared out and form like the background stars, but the newer ones, the young stars and so on, being young, are not sheared out as much. So that sort of is the story that goes around in this. Okay, so let's actually. So the next thing that I actually want to do, and I want to actually start very quickly on, is so we are actually done with the galaxies. So the second module of the course is done. So now we'll go into dynamics. Interaction. So you bunch of particles. What is the potential that a distributed distribution of stars gives you the potential, and given a potential, what are the orbits? So that's sort of the dynamics part. So let's see here. Okay. So I just now mentioned about this epicyclic theory and the fact that the stars are going around in circular orbits, right? But we know that the galaxies are made of stars and dark matter. They are not like smooth distribution of matter, right? There are stars, and so the analogy is like molecules of gas in this room. Right? There are molecules, and the other molecules know about the presence of a molecule is through collisions. What about stars? Do they collide with each other? How do they know the presence of other stars in that system? It's not through collisions, unlike in gas. It's through the large-scale gravity of the rest of the stars. Okay. So it's actually a very fundamental point, and it's a big difference between a stellar system and a gravitational system. So collisionless. Stars are collisionless. Dark matter is collisionless. They don't have strong interactions like collisions, unlike in molecules. They respond to the large-scale gravity of rest of the other stars. Okay, collisionless systems and relaxation. So you can actually think of gravity due to stars as composed of a smooth component due to all the other stars, and very jumpy discrete component due to very nearby stars. Okay, and what I'm saying in different words is that this smooth component is what dominates over this component due to short range interactions. Short range interactions are extremely rare. Okay, so that's why these are collisionless systems. Let's see. So gravity is a long range force, right? Unlike molecular forces, which are short range forces. If molecules are somewhat far away, geometrical cross section is what matters for them. But since gravitational force goes like 1 over r squared, but if you have a uniform distribution of matter, the mass actually goes like rho times, right? So the mass dm goes like rho times, so if you have, say, if you consider a mass here, oh, damn. Yeah, so, yeah. So if you consider a point here, and if you say that the mass, right, so dm is proportional to, say, there is a solid angle, delta omega times dr, delta omega times dr times r squared, right? This is the mass. If this is this size is dr, and this angle is solid angle, so you see there is this large factor r squared. If you, even if you put mass far away, there is so much of it that the large scale mass impacts you much more than the nearby mass, right? And this is because of this 1 over r squared force, or a 1 over r, minus 1 by r potential. So this is a very fundamental thing. There's another long range force that we all know. Electromagnetic, electrostatic force is 1 by r squared force. Even that has a similar characteristic. Okay, so the large scale electrostatic or electromagnetic perturbations are more important than very short range collisions in a plasma, for a typical plasma. That is, so there is a great analogy between plasmas and gravity, but there is a one fundamental difference. Yes, you can have attractive and repulsive forces in E and M, whereas in gravity, it's all attractive. So you cannot shield gravitational force, unlike the electric force, where you like polarize a medium, and if you put charge inside a conducting thing, you can hide it essentially by moving the charges around appropriately. Okay, so both are long range forces, but the shielding property in electrostatics is quite different from gravitational thing. So even mass far away at the edge of the galaxy is affecting the sun, right? So this you have to keep in mind. So the concepts that we learn here also apply in a lot of ways to the plasmas. So pay attention to this. So let's learn about something called, let's first relaxation time. So, so what is relaxation? So suppose you, in this room, if you say insert a molecule which is extremely hot, extremely high kinetic energy, right? It will not, like, after some time, it will collide with these lower temperature molecules, and it will lose energy, kinetic energy, and the molecules with which it collides will on average gain energy. So it will equilibrate with this bath. So this is what I mean by relaxation. That is, a particle encounters the other particles and share their energy, momenta, and so on, and becomes like one of them. Yeah, this is the process of reaching equilibrium. Okay, so the time scale over which such a thing happens is called the relaxation time. So let's consider a star here, and let's consider a test star here, which is approaching the star, and it has an impact parameter b. Right? You have done this problem in various avatars already. So far away from it, it has this some angular momentum relative to this point. It has an impact parameter b. It's an attractive force. So what will happen is it gets deflected. So it will do something like this. Far away from this mass, this test mass, it will just move in straight line. Right? There is no other force. let's ignore the large scale gravity due to all the other stars for now. Okay, so it goes in a straight line before and after this interaction. So you can actually think of this as some sort of a deflection. This is not quite right? It's not. So you can actually think of it as if. So I've actually exaggerated this. This has deflected an angle by it has gotten deflected by some angle delta theta. So this is the distance of closest approach. This is the impact parameter, and so on. So what we will also see shortly is that this change in velocity, right? So this is your V initial. This is a vector. So this is your V final. I mean, their magnitudes are almost the same. This is not a very strong interaction, somewhat far away. B is large. And this is your delta V. So VF minus VI. No. So this is VF, VI. So VF, right. So this is VF minus VI. So and this angle is, of course, this delta theta. We are assuming delta theta to be small. These are called small, small angle random walk. So, sometimes you'll have a mass here, sometimes you'll have mass on the other side, right? If you have a general distribution of gas, sometimes, the particle with which you're interacting is on one side, sometimes it's on the other side. So what angle it will do a random walk in velocity and in angle. So sometimes it gets deflected downwards, sometimes it gets deflected upwards. On average, if you average delta theta over many such encounters, it will be 0 because sometimes you are positive, sometimes negative, but its RMS value will not be 0. Right? This is like a standard random walk. Okay. And you see here, what's the direction of the force? So the force, the gravitational force acts in this direction at this location. It acts in this direction at this location, and it sort of acts in this direction at this location. So in the direction transverse to the direction of velocity, the force component is always towards this object, right? But in the direction parallel to the direction of motion, on this part, it's pulled towards the mass. On this part, it's pulled back, right? And you assume that delta theta is small, so you can actually think of the unperturbed trajectory and the perturbed trajectory almost along the same line. So you have a net force which is in the perpendicular direction. So you have F perp average, which is not 0, but F parallel. The force along the direction F parallel is 0, right? Parallel is like, here it's pulled towards this mass. Here it's pulled back. Okay, so let's see what F parallel is given by. So let's look at this. So let's consider all stars or all particles here have mass m, small m. Okay, so this is mass small m, this is mass small m. What is F perp? The component of the force perpendicular to the direction of motion. So that's basically, this is equal to gm squared by, let's see, let's call this distance x. Right, so gmm by b squared plus x squared. I mean, this is the force, but we are interested only in the perpendicular component. So we have to do this, if this, so let's actually draw this once more. So what we are considering is small angle deflection. So this, so you can almost think of this as it is almost not deflected from its path. So this is x, this is b. The So gm squared and times this angle, let it be theta. Okay, so the perpendicular component is cosine of theta, which is nothing but b by b squared plus x squared square root. So basically this becomes this guy, right? Simple. So this is the perpendicular component of the force. And let's say this is our t equal to 0. So at t equal to 0, the particle is at the closest approach. So we can just write x as x equals vt. At t equal to 0, it's the closest. So this is gm squared by b squared 1 plus vt by b the whole squared to 3 by 2. Okay, so what is delta v perp? Which is equal to nothing but 1 by m times minus infinity to infinity f perp dt, right? M dv dt is the force. So this is your, how much does your velocity change in this encounter in the perpendicular direction? So that's nothing but, so this integral. So you just have to write this. So this is, so gm by b squared integral over 1 plus bt by b whole squared to 3 by 2. And you have dt. So good to do a change of variable. So you just s equals vt by b and ds equals v by b dt, and it just becomes dx by 1 plus x squared to the 3 by 2. That's a standard integral. It's very easily doable. So what you get is this is equal to twice gm over b and 1 by v. You can actually see, right? So v by b, if you multiply here, and b by v, if you bring it, so this becomes like a dimensionless integral. This will give you some number, right? So then that's why you have this gm by b by v. Okay, so what we have to keep things like, what is meant by, sorry, this is small m. V is like a typical velocity of a star. Okay, a typical story, like for example, in Milky Way, you can take it as 220 kilometer per second. Okay, B is this impact parameter. So this is for a fixed impact parameter, but you can have a possible range of B. For a given B, this is how much it deflects. And you can actually think of this as gm by b squared times b by 2b by v. Actually, this is a nice way of looking at it. This is the force as if it was at a distance b, right? So this is like f perp by mass small m, and this is like interaction time, right? It only interacts for a short time when it is like at a distance of order b from this mass, right? Very far away to minus infinity or plus infinity, it does not really feel a very strong force in the perpendicular direction. So you can actually think of it like that. You can also think of it as this is v escape squared by v. So what is the escape velocity from a point mass m? V escape squared is just gm by b, right? So this is 2gm by b, right? This is the energy thing. So this is just v escape squared by v. So what it says is that the change in velocity in the direction perpendicular to the motion is proportional to 1 by v. So if v is large, deflection is less. So if you have a fast moving particle, it does not get as much deflected as a slow moving particle. Okay, and that's because it's a fast moving particle has a very short interaction time. right? So, and the other thing is if escape velocity is very high, then the gravity is very strong. So if the gravity is very strong, then delta V perp will have to be large because it's getting deflected because of gravity. Okay. What's the time cycle? 1:05. Okay. So let me actually end in 2 minutes. So here, this is called impulse approximation, right? So when we assume this angle to be small, theta, delta theta to be small, and we assume that the particle moves almost in an unperturbed trajectory. So this is called an impulse approximation. This is valid when theta is small or delta theta is small, and delta V perp is much less than V. Oh, okay. So impulse approximation is when delta theta is much less than 1, and in other words, delta V perp is much less than V. Okay, so V is the typical velocity, 220 km per second. Delta V perp is the velocity due to this encounter with a single star. Okay, so in this case, you can actually make the impulse approximation. So when does it break down? It breaks down when delta V perp is V. That is when V is of order V escape. Here, V escape is not V escape from the gravity of the full galaxy. It's due to this escape from the point mass. Okay, so we call that impact parameter as B90. 90 stands for 90-degree collision. If delta theta is small, the angle would be like a few degrees or something. 90 degrees, like you're deflected significantly. So for B90, V is equal to V escape. So that would be so what would be the value of B? So you are equating, you are basically writing delta V perp as V. So B90 is equal to twice Gm by V square. And this is called 90-degree deflection. And this is when this impulse approximation breaks down. And it's sort of easy to see, right? If you have a very fast particle, they will not, for deflecting it significantly, you have, fast particle will not be deflected as much. So for a larger V, B90 is smaller. So there's a lot of intuition in all these formulae which you should try to grasp. So this is, this calculation is for a change in velocity for a single interaction. Now what we are going, so we have done this again and again, right? Now we are going to see how many collisions do you have if you allow all the impact parameters, right? So then you sort of sum over all the possible values of B, and then you see, okay, this is on average my deflection angle, but the average deflection angle itself is 0, but it's the RMS which will increase in time. Okay, and when this RMS becomes 90 degrees, or when the RMS becomes 90 degrees, that's what is meant by relaxation. That's when you say that the star, so if you throw a star very fast at other stars, it will just sort of ballistically move. It will just get deflected a little bit here and there. But after many such encounters at different Bs with different stars, it will actually move in a direction which is different, significantly different from its initial direction. That is what is called relaxation. So we'll actually, move with this journey towards, variation of B, and then see its implications. So let me actually tell you what the implication is. So we considered all stars with the same mass. Okay, and so for example, a galaxy, it has, say, you can actually, to zeroth order galaxy is, let's say it's all, for the matter of dynamics, let's consider it's all made up of solar mass stars. Okay, and the typical velocity of these stars is 200 kilometers per second. How many such things? You have about 10 to the 10 such stars, right? So the total mass of this galaxy is n times small n. We're sort of ignoring dark matter for now. Okay, so what it will turn out is that higher the n, the number of stars in the system, the more collisionless it is. It sort of sounds very counterintuitive to you, right? Because if you have a higher number of particles, it should have more collisions. But you are also forgetting that the velocities are also set by how much mass you have. So if you take everything appropriately, the final answer is that systems which have more stars are collisionless. Okay, we'll actually come to that, but it's an extremely useful approximation, and it lets us go to this simple picture of the continuum, where you can take the mass to be distributed as whatever, 1 by r squared, NFW, this, that. Simple profiles, rather than worrying about the discrete structure of stars and dark matter. It's fundamental of galactic dynamics. Okay, so try to develop intuition for this. It will help you. So the topics that we're going to start now, this is like the basis which justifies ignoring all this microscopic structure of stars and just moving on to the continuum description. Okay, I think we'll